And I think you will present it, Emmanuel.
Yeah, thank you. Good evening, everyone. It's a pleasure
Just,
to be
just,
here
just one
today.
moment, Emmanuel. So actually, Silvia Licciardi has been a professional musician for more than 20 years, and then she went back to her first love, which is mathematics, and she studied under Pino for her PhD, and then she is now at the University of Palermo, and she now combines music and mathematics, and this is the topic that Emmanuel will talk about. Please, Emmanuel.
Thank you, Dr. Davis. Let me share my screen. Okay, can you see me?
Yes, but now we see two slides. Maybe you have to.
Oh, okay.
So then very small. So no, these
Okay.
are these are very small. Can you enlarge it a bit?
Oh, I don't think so.
No, you have to
So,
show screen or something. I don't know. Anyway, so please, yes. No, it's a bit too long. Yeah.
good evening, everyone. It's a pleasure to be here today. Before we begin, I would like to extend the greetings of Dr. Silvia Licciardi and Professor Elisa Francomano. Unfortunately, due to unforeseen institutional commitments and an injury suffered by Professor Francomano, they cannot be here with us today. I am Emmanuel Caronna, a PhD student at the Department of Engineering at the University of Palermo, and I have been tasked with presenting this work. This is the result of joint research between the Department of Engineering of the University of Palermo under the supervision of Dr. Silvia Licciardi in a collaboration with myself and the Professor Elisa Francomano and the Alfredo Casella Conservatory of L'Aquila under the supervision of Maestro Daniela Macchione. This work was realized within the framework of the Here Enacting Artistic Research project funded by the European Union. I would also like to express my sincere thanks to Dr. Yelis for the invitation and for organizing this conference. The work I'm presenting to you is titled Playing the Graph Music through Algorithms and focuses on musical analysis through the use of graph theory and neural network. Our standing dataset is very particular, a true unicum in the history of music. It consists of the variants of the arietta 1800 by Gioacchino Rossini. At the time, it was customary to leave a musical autograph, often just a few bars. Rossini, however, chose to always and exclusively use this specific text by Metastasio for different compositions. Why this text specifically? 1800 represents a sort of silent scream, a way for the author to express his own state of mind by saying, I fall silent, but in silence, I communicate my suffering to you. This provided us with a corpus of about 30 musical variants based on the same text, which was ideal for our analysis. In this first phase, we focused on the form of the aria, which involves a melodic line interpreted by a singer with attached text, and the harmonic accompaniment of the piano. I would like to highlight a crucial aspect of our research framework. While we initially selected Rossini's 1800 as our training ground due its unique variations, it represents only the starting point. It's important to stress that the entire pipeline we have developed, from the MusicXML parsing to the graph construction and neural network analysis, is completely reproducible and agnostic. The method is not tailored specifically to Rossini's style or to operatic music. It's a general-purpose tool designed to work with any type of score and composer and the musical style. Whether we feed it Bach, Mozart, or contemporary composition, the algorithm can construct the corresponding graph and extract the structural feature without any modification to the core architecture. The data initially arrived in Sibelius format. The first fundamental step was transforming this score into a format interpretable by our algorithm in Python and MATLAB. An important aspect of our method is that we worked in parallel, developing the code in both MATLAB and Python. This served to validate the result, obtaining a consistent output from two different environments, confirmed the correctness of the algorithm. We choose the MusicXML format as it allows us to have a nested and explicit representation of all the information contained within the score. However, MusicXML is very verbose. Even to describe a single note, many lines of code are necessary. In this example, we can see the specific representation of a quarter note, A, in the fourth octave, linked to a syllable, Mi. We therefore performed a parsing operation to extract only the essential information: pitch, octave, duration, and the associated syllable, reconstructing everything into an interval representation manageable by our software. Given the nested nature of a musical notation, we decided to represent the scores using graph theory. In this representation, the notes and syllable become the notes, while the temporal or structural relations become the edges. Let's answer a fundamental question. Why graph theory? Usually, music information retrieval relies on audio analysis, which treats music as a sound waves, losing the symbolic meaning. Or it uses sequential models like RNN on MIDI files, which are great for melodies, but struggle with the complex vertical simultaneity of polyphony. We choose graph because music is not just a sequence, it is a structure. Graph allows us to preserve the relationships between a syllable and a note, or the harmonic interval between two piano notes without flattening the information. Here you can see a first example of a graph representing exclusively the melodic line with its sequential nature. Zooming in, we can observe the temporal sequence. Starting from the initial rest, arrive at the first actual note of the song that we can see just here. Subsequently, we integrated the text line where each note represents a syllable. The edges are directed forward precisely to represent the temporal succession of the syllable. In this graph, we see the actual construction of the graph. We see the interaction between the nodes in red, and the syllable node in yellow. The edges also play a fundamental role, as the red edges indicate the connection from a note to its consecutive note, and the yellow node represents the connection from a syllable to its consecutive one. Meanwhile, the orange edge indicates the connection from a note to its syllable. To the representation of the melodic line alone, we also added the piano harmony, which follow the same logic. In fact, the green nodes represent the notes of both the right end and the left end of the piano, and the actual structure is provided by the addition of the undirected green edge, which has the task of creating the vertical simultaneity of the piano notes. The visualization in MATLAB confirms what was just said and schematically shows the melody line in blue and the syllable line in green. You will notice some values are indicated as null. These are not errors, but represent grace notes that don't have a pre-established metric duration. Once the score is structured as a graph, all information is intrinsic to the structure itself. We can therefore extract statistics simply by analyzing the property of the graph. For example, here we see a color map based on the density of the nodes, meaning the number of incoming and outgoing edge, the degree of the node. The nodes in darker colors, red, are those with more connection. Visually, this corresponds the syllables that bind more complex group of nodes. This type of visualization makes the understanding of structural complexity immediate even for those who don't read music. We can indeed see how, on average, almost all notes have an incoming edge. This means every note is preceded by another note, with the exception of the first one, which is why we see 0.99 and not 1. And in particular, we can note how an average 2.47 syllables are associated with each note. In this example, we can see all the syllable note da has a degree of 7 precisely, because the 7 notes which are part of melisma are connected to this syllable. To best study the distribution of notes and melodic leaves, we decided to identify three pitch families based on the MIDI representation of the notes. Low for the grave notes, mid for the medium register, and high for the acute register. Meanwhile, for melodic leaps, we used the term step to represent a leap of a second, and the leap to represent a leap greater than a second. This allowed us to easily identify the character of the piece and the voice of the singer performing it. In this example, we see how the piece has a medium texture with note of predominantly short and mid duration, but with several episodes in the acute register identified by high. This suggests us easily that it is a piece of medium speed entrusted to a female voice, hypothetically a soprano. Another interesting datum concerns the distribution of vowel duration. This has an interpretative fallout. Knowing if a vowel, like an A or an O, is statistically longer or shorter in certain contexts can guide the singer's expressions. Shifting attention to the textual component, this heat map allows us to visualize the distribution of transition between contiguous vowels within the syllables. Practically, we are analyzing the phonetic sequence. Given a syllable note with a certain vowel, what is the vowel of the next syllable? As you can see, on the vertical axis, we have the starting vowel, outgoing vocal note. On the horizontal axis, the arrival vowel, incoming vocal note. The red color indicates frequency. The more intense it is, the more often that specific transition occurs in the text. For example, we immediately notice a stronger recurrence in the passage from the vowel A to A with a value of 8, or from E to A. Conversely, the light or white cells indicate the transition that, in this specific corpus of variants, never occur. After analyzing the individual score, we moved on to analyze the dataset in its entirety, about 30 scores, divided into stylistic families. To do this, we used neural network, and specifically graph neural network, given that our data was already structured as graph. Our main objective was not simple supervised classification, but unsupervised clustering. That is, we wanted the network to autonomously find the similarities and hidden patterns among the pieces, without us telling it a priori, this is a bolero written by Rossini, or this is a canzonetta written by another composer. To analyze the entire dataset, we adopted an hybrid graph neural network. The landscape of this network includes various architectures, such as a graph convolutional network or a graph attention network. However, our implementation is based on two fundamental pillars: GraphSage and the message passing neural network. We chose GraphSage for a practical reason: scalability. Thanks to its sampling system, it allows us to efficiently manage large graphs, which is essential when increasing the dataset. The message passing, on the other hand, constitutes the engine of our model. They provide us with the general framework to define exactly how the messages, that is the musical and the textual information, must travel and aggregate among the nodes of the graph. I would like to make an important clarification regarding the data. We started from a core about 13 original scores by Rossini. However, as you know, neural network requires a large volume of data to learn effectively. For this reason, we applied data augmentation techniques, generating variations that allowed us to bring the dataset about 1,000 scores. With this enriched dataset, the network architecture, which you see schematized here on the right, can be directed toward two main objects. Supervised classification, where we provide the network with already labeled data and teach it to recognize predefined categories. And unsupervised clustering, which is the aspect we focused on most in this phase. In this case, we don't give any labels to the network. Instead, we ask it to analyze the structure of the graph, therefore harmony, tonality, rhythms, and to group the pieces autonomously based on their similarities. In the diagram, you can see the flow. It starts from the input features, our graph, passes through convolution and Pulik layers, until arriving at a final embedding that is a compressed and mathematical representation of the score, which is then used to classify, or in our case, to create class. But how does the network actually learn? In the case of supervised classification, our goal is to train the model so that the error between its prediction and the real data is the lowest possible. The three-dimensional graph you see on the right visually represents the concept. It is the surface of the cost function or loss function. To train the network, we use mathematical methods like gradient descent. In simple terms, the algorithm calculates the slope of the surface and takes iterative steps to descend toward the global minimum point. Reaching this minimum means having found the optimal parameters that minimize the approximation, allowing the network to correctly classify the pieces. This diagram illustrates exactly how we implemented our architecture. The processing flow proceeds from the left to the right. Heterogeneous input on the left. As you see in the input column, we don't provide the network with only nodes. We pass it a rich set of heterogeneous information, piano features, syllable features, vocal notes, and even embedding that encode the harmonic context, such as Roman numeral analysis and tonality. The encoder in the center left, there are raw data passed through encoder. Their task is to translate this different information, notes, text, harmony, into common mathematical languages, creating what you see in the diagrams as hidden states, the green block. Heteroconv and graph stages in the center. Here the magic of message passing happens. We use a heterogeneous convolution module based on graph stage. Why heterogeneous? Because the network does not treat all connection in the same way. As you read in the central box, the network learns by distinguishing relationships. It learns how a note influences the next note. But separately, it also learns how a syllable influences the note. It is sung on, syllable, sung on, note, or how the piano interacts with the voice. The output on the right, after aggregating all this stratified information, we obtain a final representation that is used for clustering, allowing the network to group pieces by styles, harmony, and tonality without the need for human labels. These are the first results. Although the silhouette score about 0.5 indicates that there is still room of improvement, the network effectively divided the dataset into two main clusters. Analyzing the data, these two clusters correspond coherently to the two main stylistic forms present in the Rossini dataset, the bolero and the canzonetta. It's important to note that the network made this distinction autonomously, choosing the number of clusters to create on its own. We then pushed the experiment further, introducing external data to test the system's robustness. In this graph, we introduced a piece by Puccini into the Rossini dataset, and the network recognized the foreign style and created a third cluster, the blue points, separating it from the Rossini cluster, green and orange. Furthermore, we tested the network with unbalanced dataset, for example, more canzonetta than boleros. Despite the imbalance, the network maintained the ability to recognize and separate the classes correctly. We let the system automatically, again, decide the number of classes, their recognition, and it adapted correctly to the structure of the provided data. In conclusion, we are looking to refine these models and compare them with other datasets. The future goal includes the use of generative GNN to explore possible similar composition forms. However, I want to emphasize our philosophy. These tools serve to analyze and understand the creative process, but nothing can ever replace the intuition, uniqueness, and creative spark of the human being. Thank you all for your attention.